Hello and welcome to our lab on capacitance. Now today we're going to be charging and discharging a capacitor. And so let me sort of tell you some of the terms associated with that. First of all, whenever you have a capacitor, let me draw a schematic diagram of what the capacitor looks like. You have a wire, a straight down line, and then sort of a curved line like this. And when I draw that, that means that the curved line is my negative side, and the straight line, that's my positive side. And so whenever you're doing experiments using electrolytic capacitors, and it's telling you which side is negative, which side is positive, it's very important to make note of that convention. Because if you get a capacitor turned around the wrong way, it becomes a tiny firecracker. And so we want to be careful with the setup in today's lab. If you're not sure, if you have your capacitor turned correctly and this side is facing the negative terminal of the battery, this side is connected to the positive terminal of the battery, either side through the resistor, then bad things will happen again. So check with your lab instructor to make sure before you actually connect it to the battery. So we have this little electrical component called the capacitor. It's C for capacitor. And its unit is the farad. And so you might say my capacitance, I have a capacitance, so my capacitance is equal to maybe 30 microfarads. And the micro there means times 10 to the negative 6th. And so that would be 30 times 10 to the negative 6th farads. And so that will be a typical capacitor value. Now, the relationship between capacitance and voltage goes like this. The capacitance multiplied by the voltage across the capacitor, and this is something we can measure with a meter, this voltage is equal to the charge on the capacitor, Q. And so you're probably familiar with Q. Q is the amount of charge, all right, stored on the plates of this capacitor. And so a capacitor has a certain capacitance based on the amount of charge that it can hold for a certain voltage. Now, if that capacitance is a fixed value, right, it has some sort of dielectric in here or whatever, and it's a certain capacitance. This is a 30 microfarad capacitor. That doesn't change. That's a constant. And so you can see that as you begin to put charge on the capacitor, its voltage is going to go up. If charge is removed from the capacitor, its voltage will be decreased. So there's a direct relationship between voltage and charge. Now the charge on a capacitor can't be instantaneously put on. Right? The charge has to, it takes time for a capacitor to charge. And so what we want to do is look at some equations that model the charge and the discharge of this electrical component called the capacitor. So if I start charging the capacitor, well, I don't have an instrument that I can use to measure charge, but I have readily available an instrument to measure the voltage. And remember, the voltage is directly related to the charge. And so as the capacitor charges, let's say we start here at 0 volts, and up here we've got some maximum voltage. Let's say this is the voltage of our battery. If we have a 1.5 volt battery, this is the maximum voltage that our capacitor can charge to, 1.5 volts. So if maybe it's a 6 volt battery. Okay, so this will be our maximum possible charge. And so as it begins to charge, it charges rather quickly at first. But as time goes on, that charging rate decreases, and eventually it will get really close to the battery voltage, maybe not all the way there. But this is what the charging curve will sort of look like, and we'll be able to plot that in lab. But the equation that models a charging capacitor is this one. The voltage at any time across the capacitor, as we measure it, is equal to some percentage of the battery voltage. So the battery voltage, and we actually use this equation to model it, 1 minus E to the negative 1 over RC times T, time. And so we'll examine this stuff in the exponent first, but here's time. So we're plotting this versus time. And so as time, let's check our initial conditions. When time is equal to 0, then this whole term goes to 0. So e to the 0 power is pretty much what anything to the 0 power is, which is 1. And so 1 minus 1 gives us 0 in this term, and 0 times the battery voltage is 0. So when time is equal to 0, that means the voltage across the capacitor is equal to 0, which is why we want to start with a discharged capacitor so that this model works. But now, as time gets very large, maybe goes toward infinity, this will be a very large negative term. So this is this minus sign. So as t goes to infinity, this goes to negative infinity. And so anything to a negative large number is actually a small number. So as this goes to e to the negative infinity is actually pretty real close to 0. So 1 minus 0 is 1. Battery voltage minus 1 is equal to the battery voltage. So you can see as time goes to infinity, our capacitor voltage, okay, we're plotting up here, this is the capacitor voltage versus time, that's the name of this plot, then we're approaching the battery voltage as t equals infinity. So this is a charging capacitor. Now the equation's a little bit different for a discharging capacitor. So let's look at a discharging capacitor. Now when we start to discharge our capacitor, we're going to start with a capacitor that's fully charged. So it's going to be at the battery voltage, so that's where we want to start. And it's going to start discharging rather quickly, but as it loses charge, that force decreases, and so it begins to charge at a less and less quick rate here. And so the voltage across our capacitor is modeled like this. Again, it's some percentage of the battery voltage, but this time it's time, so the 1 minus is just e to the negative 1 over RC times time. And so as we model that, you can see that when time is equal to 0, e to the 0 power is 1, and so VB times 1 is equal to VB. So when time is equal to 0, our voltage across the capacitor is the battery voltage. But as time goes on to infinity, this becomes e to the negative infinity, or 0, and so it approaches 0 as time progresses. And so these are the equations that we use to model the charge and discharge of a capacitor. So let's take a look at this in the exponent here again. We have negative 1 over RC times T. Let's examine these terms. The R in here is the resistance of the circuit. And in today's lab, you're going to have a resistance of 1,000 ohms. Ohms being the unit of resistance. Okay, that's a given. But you're not going to know what C is. And so the way that you'll find out what C is once you have your data, you're going to plot it, and this is called a natural exponential curve. You're going to plot your data in log pro with a natural exponential curve fit. That curve fit has certain parameters. It has A, is A to the times e to the negative, or C, T, plus B. So your parameters A, B, and C sort of describe the curve fit. So this parameter that's to the exponent of the E, I think log pro calls it C. Don't get that confused with capacitance C. It's just a parameter, A, B, or C. It's not capacitance. But that parameter, you see, is equal to 1 over RC, where R is resistance, C is capacitance. And so once log pro gives you that parameter, then if you know what R is, you set that parameter equal to 1 over RC, and then you know what R is, you know what the parameter is, log pro gives it to you, solve for C. That's an accurate way of determining the capacitance of a circuit. Because capacitors will have their value printed on them, but usually capacitor values are wildly inaccurate. 25–30% is not irregular for as far as the accuracy of the printed capacitance goes. And so if you don't have a meter that reads capacitance, which we don't, then you have to do this in order to determine the exact or a more precise or more accurate capacitance of the circuit. So you do this experiment and then solve for C, the capacitance, and now you've got an idea of the capacitor that you have. And so you'll be doing this with two different capacitors. So you'll be discharging two capacitors, determining the curve fit parameters, and then so you'll have two capacitors where you actually know the capacitance. And then we're going to use those two capacitors and say, well, what do we predict would be the total capacitance of a circuit if we put those in series or parallel? So let me draw this out. You have two capacitors, and let's say we put them in series. Series means that one follows the other. There's only one path through here. So it's a serial connection. Series, one after the other. And so let's call this CA and CB. Capacitor A and capacitor B. Well, theory predicts that the total capacitance, C total, is going to be equal to, okay, and let me just make some room and write it out like this. It works like this. 1 over C total is equal to 1 over CA plus, I guess I should keep that a lowercase a, 1 over CB plus, and as many capacitors as you have in series. That formula holds true. So you should be able to predict, based on what CA and CB are from when you determine those values from the curve fit, what our total capacitance is when you place them in series. And you'll actually put the two capacitors in series electronically and do the experiment again. You do the discharge experiment again, curve fit it, and you'll get a value for your total capacitance. And then say, was it close to my predicted value? Hopefully yes. There's another way that you can connect those capacitors together, and that is in parallel. And again, I won't go into the theory behind the equation. You'll do that in lecture. But if you have a parallel connection, and say you put one capacitor up here and another capacitor down there, we'll call this capacitor A, this is capacitor B, and the positive ends are connected together, the negative ends are connected together, okay, but there's a choice. You can branch and go either way through a capacitor. So these are said to be in parallel instead of in series. And so theory predicts, okay, and you'll talk about this theory in class, that the total capacitance is equal to the sum of CA plus CB plus any number of capacitors that come afterward. And so what you'll do is you make a prediction of what the series, what this parallel total capacitance is, and then design the circuit. You put these two capacitors in parallel and plot a voltage versus time curve, fit the exponential to it, determine the capacitance of that circuit, and then see, did that work out? Is it really just the sum of these two capacitors? You'll be able to determine that experimentally. All right, let's take a closer look at our apparatus. First of all, I have a lot of alligator cables that I can use to make my connections with. I have a battery. In this case, this is a 6-volt lantern battery, and on top you can see where the positive terminal and the negative terminal are. It's labeled positive 6 and negative. You may have a different battery, but be sure to identify right off the bat what your positive and negative terminals are. This is our resistor. It's just a large ceramic resistor, and it's rated at 1 kilo ohm or 1,000 ohms. And last of all, our capacitors. And these are the capacitors. And you see on one side of the capacitor there is this sort of a dashed line. I don't know if we can focus on that, but it's a dashed line that indicates that this is the negative side. The other side is just plain. That's where the positive side is. So it's sort of a strip with a little negative sign, a little bubble almost. That's the negative side of the capacitor. The same with this one. There's a little strip there indicating the negative side of the capacitor. The other side is just blank. So this terminal is negative. So when I make that connection, I want to make sure that I take this negative terminal and go from that to the negative terminal of the battery. If I get this turned around, then that's actually very dangerous. This could heat up and explode. So you have to be careful that you get it oriented the right direction. Now, as far as the rest of the circuit, according to our circuit diagram, we want to put this in series with the resistor. And so I'll do that. I'll put it from this side to the resistor. And then the resistor connects to the positive terminal of the battery. And so I'll do that. I'll connect it to the positive terminal of the battery. Well, actually I won't yet because, well, let me go ahead and do it. And so what's happening here is I'm charging this capacitor. As soon as I connected that, the capacitor started to charge. Now I want to look at the voltage across that capacitor. And so I have this vernier differential voltage supply. It goes up to 6 volts, so I'm okay with my 6 volt battery. And so here's positive and negative. This is the negative terminal of the battery, so let me trace it down here to the capacitor, and I'll clip it on to that alligator lead right there. Now, and this is the negative side of the capacitor. Now the positive side here, I'll clip this positive terminal of the voltage differential voltage probe over to there. And now if there's voltage on that capacitor, this is reading it. And you can see down here in the lower corner it's around 6 volts. So when I collect, I want to discharge the capacitor. The way I discharge the capacitor is I disconnect the battery terminals and I put them together. This takes the battery out of the loop and the capacitor begins to discharge. So let's do that while we'll watch it on the screen. I'm going to hit collect. And I'll take this off and I will clip them together. And our capacitor is discharging. And you see it makes that exponential curve. If I wanted to charge it now, I would just reconnect my battery terminals. And I'm charging the battery now. And so, so now I've got this beautiful discharge curve. And I can go into my curve fit. And I can fit that to a natural exponential. And it's going to give me my parameters. And the parameter that's in the exponent of E, then the power of E, is going to give me information about the capacitance of the circuit. And so I can do this with the other capacitor. I can do it with 2 capacitors in series. I can use my alligators to connect these in series. I can get creative and connect these in parallel with each other. Kind of put these negative ends together and clip them with one of your little leads. Put them in parallel. All right, so these are parallel capacitors here. And then make sure your negatives are on the same side and toward the battery. And so that's it. I can look at different configurations of these 2 capacitors and accurately determine their capacitance using Log-A-Pro's curve fitting feature. Alright, so I've sort of described for you what goes on your tabletop when you're charging and discharging a capacitor. But there's an experiment that we can do that the whole class can do together. And I think we'll do that first in order to sort of get you acclimated into this idea of watching a charging and discharging capacitor curve. And that is, we have this set up here. I've got a power supply, a resistor box. My capacitor is this blue thing here. The capacitors are rated at, it's around 22,000 microfarads. How accurate is that? We'll see. 22,000 microfarads. Our resistor is going to be 1,000 ohms, just like the resistor at your table. There's a resistor in here that we're using. And then I have my switch, so I can charge the capacitor or discharge it. Now, to measure the charge and discharge curve of the capacitor, you are going to watch a projection on a screen behind me. And as it charges, that needle will go from 0 all the way up to 100. Okay, 100 volts, I guess we could say. And so as it does that, we're using a split timer. You can see, starting at time equals 0, you can get time at 10 volts, 20 volts, 30 volts, 40 volts, 50 volts, 60 volts, all the way up to maybe 90 volts. And then you can do the same thing charging from 100 down toward 10, or past 10 to 0. And so by doing that, you can then plot that data, voltage versus time in log or pro, and sort of verify that charging and discharging do model well using our inverse exponential and natural exponential curves. So sort of an example of what that looks like. You can see behind me on the board, well, I don't know if you can see it, is the charge and discharge curve. And now as I throw the switch, you can see it beginning to charge. And you see you're in there with your split timer and you're going 10, all right, here's the time at 10, here's the time at 20, here's the time at 30. And it gets slower for each increment of time because it charges more slowly as it finally reaches that maximum voltage of the power supply. So this will be a fun experiment to start off with and make sure everybody is on the right page, and then you can go back to your tabletops and do the same sort of thing using your own discrete electronics components and your own battery and your own voltage measuring device.